Hey guys, so in this video we're going to be talking about dehydration and overhydration and how our body regulates osmolarity within the different fluid compartments. So first I just wanted to start off with this chart. This is going to be the general way in which we represent the different fluid compartments and what's happening within all of them. Essentially on this side we have our intracellular fluid compartment, which that's literally the fluid inside your cells, right? And then our extracellular fluid compartment is the fluids on the outside of your cells. Pretty self-explanatory. Within the ECF, we have the fluid that's in the plasma and then the fluid that's in the interstitium. So these all have different percentages, and it's actually pretty important for you guys to know the different percentages. So plasma is 5%, interstitial is about 15%. So together the ECF is 20%. ICF is composed of 40%, and this whole thing together is called your total body water, and that's about 60% of your body weight. So all of these are percentages of your body weight. So if, for example, you're given a question with a person who is 65 kilograms. 65 kilograms is equal to about 65,000 grams, right? If we want to calculate the amount of plasma in milliliters that this person has, we are going to take that 65,000 grams and multiply it by 5%, which is 0.05. And so 65,000 grams times 0.05 is equal to 3,250 grams. And grams is equal to milliliters, right? So that's 3,250 milliliters of plasma would be the answer. I do want to just briefly talk about dehydration versus overhydration. So dehydration, we're always talking about losing something, whether that be sodium, water, or sodium and water. It's always talking about the loss of one of those things. Overhydration is the exact opposite. We're always talking about gaining something. We're either gaining salt, gaining water, or gaining both at the same time. So this is the way I draw all of these charts that have the different fluid compartments, and I like to draw them all together so I can compare and contrast at the end. I think it'll make it a little bit easier for you guys to remember. Okay, so we're just going to start in this top left corner. So first off, we already defined dehydration is either the loss of salt, water, or both. So we're always losing something. And I should note also that whenever we're talking about the loss or addition of anything, it's always going to affect the extracellular fluid compartment first. So the ECF is always going to be what's affected. That's our plasma. So obviously if we're adding fluids, it's going to affect our plasma before it's able to get inside the cells, right? So we're always going to be affecting our ECF first. So dehydration, it's always the loss of either salt, water, or both. So from the ECF, I'm going to draw a little arrow going out. Overhydration is always gaining something. And again, it's always going to affect the ECF first. So we're going to draw a little arrow in just to remind us that this is what has to happen first before we get any of these other things going on. Okay, so starting in the top left corner, and that number 300 I put is supposed to represent osmolarity. So your body is about 300 milliosmoles. It's actually closer to about 308, but this is going to make the math a little bit simpler so I can kind of show you guys what's going on. Okay, so 300 in both the ECF and ICF. If one of those numbers change, the fluid from the other compartment will compensate to even them out again. We can't ever have an osmolarity of 301 and then 320 in the other. Instead, we would have an osmolarity of about 310 because the other compartments are going to compensate. Okay, so starting with hypoosmotic dehydration, which is the one in this corner right here, we are going to be losing something. So if we are hypoosmotic, that means that we are going to be decreasing our osmolarity, right? So we need to take 300 down to something below 300. In order for this to happen, that means that we have to either be gaining water or losing salt. And we know that we have to lose something, right? So we are going to be losing salt here. I'm going to put it as losing sodium chloride. Okay, so if we lose salt, that's going to bring our osmolarity down a little bit. So say we are down to 280. You can't have an osmolarity of 300 on one side and 280 on the other side. The compartments are going to compensate. And the way we do that is we're actually going to shift fluid from the area of low osmolarity to the area of high osmolarity. So the ECF will add fluid to the ICF. And whenever that happens, it's going to change our osmolarities again. And instead of being 280 on the ECF side, it's going to be about 290, and the ICF side will be equal, right? Because we have to have the same osmolarity on both sides. And in addition to that, we are adding fluid to the ICF side. So whenever we draw our lines, we're going to show an expansion on the ICF side and a contraction on the ECF side, because again, we're losing fluid from that side. And then the osmolarity is going to be slightly under 300. So it's no longer 300, right? It's 290. Okay, moving on to isoosmotic dehydration. And this one is actually really easy. But if you guys think about isoosmotic, right, that means that the osmolarity isn't changing. So this number 300 isn't going to change. And the way we are able to do that is we're actually losing salt and water equally. And whenever that happens, again, osmolarity isn't going to change, but we've lost water, right? So we're going to show a contraction of the ECF compartment. ICF isn't going to change because, again, this stays the same. So our ICF compartment actually stays at the same volume. So we're only just going to have this one line. So it's pretty simple. Moving on to hyperosmotic dehydration. So the way we are going to make the ECF hyperosmotic is we're actually going to be losing water. And that makes sense, right? Because in this first one, we lost salt. The second one, we lost both, so the only one left to lose is water, right? Whenever that happens, we're actually going to be causing that 300 to go up a little bit higher, become hyperosmotic, so maybe it's 320 now. Now again, whenever that happens, you're going to have water from a low osmolarity shift to the high osmolarity. So fluid from the ICF is going to shift to the ECF. And whenever that happens, we're going to change our osmolarity again, so maybe now both sides are equal to about 310. So better than 320, but again, still higher than our initial 300 level value. So this would be considered hyperosmotic. We're moving water from both the ICF and the ECF, so we're actually going to show contraction of both sides, and it's hyperosmotic, so it'll be above that initial line. Moving on to hypoosmotic overhydration, and if you guys recall, we have to be adding something here. In order to make it hypoosmotic, you're going to have to actually be adding water. Whenever we add water, again, it's going to be hypoosmotic, so maybe now it's about 280. Water is going to shift from low osmolarity to high osmolarity. Whenever that happens, we're going to change our osmolarity to maybe 290 and 290. So still hypoosmotic on both sides, but better than 280. So we're going to have that line below. And again, we've gained water in both the ECF and the ICF. So whenever we do that, we're going to show expansion of both sides, just like that. Moving on to isoosmotic overhydration. So with this one, in order for it to be isoosmotic, we're going to have to add the same amount of water and salt equally. So whenever that happens, osmolarity is not going to change, and the only thing you're going to get is an expansion of the ECF. ICF won't change because the osmolarity is not changing, so there's no reason for water to shift. Moving on to hyperosmotic overhydration. So the only one that's left is to add salt, right? Because we added water here, both here, and this one's the only one that's left. But if you want to check me on that, it's hyperosmotic. So in order for something to become hyperosmotic, we need to either add salt or take something away like water. And since this is overhydration, we know we're going to have to add something. So that's adding salt. Once we add salt, we're going to change the osmolarity. Maybe this one now becomes 320. Water is going to shift from the low to the high. And whenever that happens, we're now going to change osmolarity once again. Osmolarity is going to become maybe 310 on both sides. And so osmolarity is low, right? Osmolarity is high, right? Because we were at 300 and now we're at 310. We added water to the ECF side, so we're going to show expansion on that side. And because we've added water, we've moved water from the ICF to the ECF. That means we're going to be losing water on the ICF side, so we're going to show a contraction on that side. And one last thing I wanted to cover is the situations in which these things happen. So hypoosmotic dehydration, we are losing salt. The high yield situation where that happens is actually a decrease in aldosterone. So primary adrenal insufficiency or some sort of aldosterone deficiency could potentially cause this, right? Cause this hypoosmotic dehydration. Isoosmotic can actually be caused by three really high yield Ways, the first is hemorrhage. Second is through burns, where you're leaking in abundance of plasma. Third is through vomiting and diarrhea. Kind of lump them together because they're similar, right? And this makes sense, right? Because our blood, our plasma, and our excretant is going to be composed of equal amounts of sodium and water because it's coming directly from our fluid compartments. So all of that stuff is going to be equal to 300 milliosmoles. So it's going to be isoosmotic. Hyperosmotic, the way we do this is we have to lose water, right? So there's actually a couple different ways we can do this. Diabetes is the first, so diabetes mellitus, diabetes insipidus, which is a different disease, right? This one has to do with high amounts of glucose. This one has to do with not responding to ADH, yeah. And then one last thing is alcohol. And alcohol actually does a similar thing that diabetes insipidus does, is it is able to inhibit ADH, which is why we pee a lot when we've been drinking too much. Hypoosmotic overhydration, the scenario when we have added H2O, the first one is pretty simple, right? We can just drink too much water. Another way we can do this is getting hypoosmotic fluids. And then the third way is something called syndrome of inappropriate ADH. And syndrome of inappropriate ADH is when we have too much ADH. So it's kind of the opposite of diabetes insipidus. If we have too much ADH, then that means we're not peeing off enough water. So we're actually reabsorbing more water, which is going to lead to this hypoosmotic overhydration. The isoosmotic overhydration, the scenario in which we get that, is too much normal saline. So normal saline is actually isoosmotic. So if we give too much, then obviously we're going to have increased fluids, same osmolarity as our body though, so we're only going to have expansion of the ECF, not the ICF. Hyperosmotic overhydration can be caused by anything that's going to add salt, right? So one of the ways we can do this is actually too much aldosterone. So in hypoosmotic dehydration, we didn't have enough aldosterone. In this one, we actually have too much. And that makes sense because aldosterone is responsible for reabsorbing sodium and secreting potassium. So if we don't have aldosterone, or if we have too much aldosterone, we're going to be absorbing a lot of sodium, which goes with the hyperosmotic overhydration. Another way we can get this is if we give hyperosmotic fluids, right? Okay guys, this concludes the video. I hope it helped. Please feel free to leave a comment and don't forget to like and subscribe. Thanks.